Hi, thanks for joining me. Today I'm going to be doing a Putnam problem, and this comes from the 2015 paper, and this is problem B1. Suppose we have a function f which is from the reals to the reals, and it's 3 times differentiable, and it has the property that it has 5 distinct real zeros. So it has 5 distinct numbers, real numbers, which when you plug into f you get 0. We want to prove that this kind of function here, so f plus 6 f prime plus 12 f double prime plus 8f triple prime, where the prime represents derivatives, this function here, we want to show that it has at least 2 distinct real zeros. Okay, so if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so remember we want to show that this guy here has at least 2 distinct real zeros. Now the way we're going to do that, well, firstly, is we're going to state and prove a lemma. I claim that if we have a function h of x which is real to real and is at least 3 times differentiable, and it has the properties that it has a property that has at least 5 distinct real zeros, then h triple prime of x has at least 2 distinct real zeros. And it's quite clear to see that this, if we can prove this, it will help us to prove, or to perhaps think about the problem that we have at hand. Now the way we prove this is essentially just repeated application of Rolle's theorem. So if you've not seen Rolle's theorem before, I'll essentially give a hand-wavy proof of this thing here, but it basically just says that if you've got a differentiable function which has, say, 2 roots here, it doesn't even have to be 2 roots, 2 points at which it has the same value, then somewhere in between there's got to be a point where that function has derivative 0. Okay, so if you think about this guy here, h of x, let's suppose it has 5 real zeros, so let's just give a sketch of it. Let's say it looks something like that, maybe it does that, that's 1, 2, 3, 4, and let's say it does that, like so. Okay, so this is perhaps an example of h, and then what we're going to do, these are its 5 roots. Now Rolle's theorem says that between any 2 roots, there's a point where that function, at least one point where that function has derivative 0. So if this is h of x, okay, then we can see, for example, here, oopsie daisy, here, 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 and here, that h prime of x is 0. So in this case, we have h prime of x has at least 4 distinct real roots. Well, then we can repeat this argument with h prime of x now instead of h of x. If h prime of x has at least 4 distinct real zeros, then that means the derivative of h prime of x must have at least 3 distinct real zeros. So that means h double prime has at least 3 distinct zeros, and then continuing one more time, we get that h triple prime, this guy here, has at least 2 distinct real zeros, and that's kind of a proof for this theorem here. Yeah, if you want to see perhaps it's in a bit more rigor, look up Rolle's theorem, but this is essentially a repeated application of Rolle's theorem, but hopefully this diagram helps to paint the picture. Okay, so I'm going to consider this proven. We've shown that h triple prime has at least 2 distinct real zeros. Now we want to use this theorem, or this lemma, but we can't just apply h, sub in h equals f, because then we're only going to get information about f triple prime. We don't want information about just f triple prime, we want it about this combination here. So we want to find some function h of x which kind of has this guy here as its third derivative, or something like this. And the way we're going to do that is by introducing sort of a multiplicative factor. Let me clean up the whiteboard and I'll explain what that means. Okay, so now what we want to do is actually introduce a function h of x which we're going to write in terms of f of x, and then what we'll do is look at the third derivative of h and hopefully get something that looks a little bit like this. So what we want to do is write h of x as something times f of x, and this something here is like a multiplicative function, and we want to have a think about what we can multiply f of x by, so that when we take its derivative 3 times we get something like this. Hopefully if you think about it for a few seconds, you see that a good candidate is something like e to the alpha x, where alpha is just some real number which will work out. Okay, so I claim that h of x equals e to the alpha x f of x is a good place to start. The reason for that is, firstly, we like exponentials. They're always positive, which means firstly it's not going to have any interference with the roots, because we know clearly if f of x is 0 then h of x is 0, but also the reverse holds. If we have some x naught such that h of x naught is 0, then because this guy here is also positive, that tells us that f of x naught is 0. So putting those 2 pieces of information together, we get that f and h share the same roots. So because we know that f has at least 5 distinct real zeros, that means h has at least 5 distinct real zeros, so we can apply the lemma that we just proved. But also the reason we like these exponentials is because they're infinitely differentiable, and so clearly this guy here is also at least 3 times differentiable, which is what we needed for the previous lemma as well. Okay, so let's go ahead and just differentiate h of x 3 times. I'm not going to work out h prime and h double prime, I'll leave that to you, but let's just write down h triple prime of x, and maybe you've seen this before, it's a nice little trick. It's going to look a little bit like binomial coefficients. So if you just take the third derivative, you're going to get alpha cubed f of x plus 3 alpha squared f prime of x plus 3 alpha f double prime of x plus f triple prime of x, like so. Okay, so h triple prime of x is e to the alpha x times this guy here, alpha cubed f of x plus 3 alpha squared f prime of x plus 3 alpha f double prime of x plus f triple prime of x, and it looks very similar to sort of binomial coefficients if you've seen that before. But yeah, just to get this, you just do the 2 intermediate steps of taking the derivative. But I've skipped that for this video. And now what we want is we want this guy here to look a little bit like this. And we can see the thing inside the square brackets kind of does, except now we've got alphas instead. Now if we just look back to this, what we want to have, the coefficient of f here is sort of 1, and we see the coefficient of f prime is 6. So there's a 1 to 6 ratio between the coefficients of f and f prime. So we want that ratio to uphold in this case. So we want alpha cubed, so we want 3 alpha squared, sorry. So the coefficient of this guy here to be 6 times the coefficient of the f of x. So we want 3 alpha squared to be equal to 6 alpha cubed. Then just rearranging this and dividing by alpha gives us that alpha is equal to a half. So dividing both sides by 6 gives us 3 over 6 alpha squared equals alpha cubed. Dividing both sides by alpha squared, alpha equals 3 over 6, which equals a half. So that tells us that alpha equals a half is perhaps a good sort of plugging alpha equals a half into this e to the alpha x suggests that this would be a good candidate function. Let me clean up the whiteboard. I'll plug in alpha equals a half, and then we'll see there's a tiny bit of manipulation we still have to do, but then we'll get the desired result. Okay, so let's remember when we introduced h of x, we had this multiplicative function e to the alpha x, and we had alpha just kind of being a free parameter which we were able to choose, and we just showed that if we wanted this to be a sensible multiplicative function, we must have that alpha equals a half. So let's suppose we plugged in alpha equals a half, then computed the 3 derivatives like so. So basically we get this, but we have to plug in alpha equals a half. So we get this is e to the x over 2. A half cubed is just an eighth, so an eighth f of x, plus 3 times a half squared is 3 over 4. So 3 over 4 f prime. 3 times a half is just 3 over 2. That's f double prime. And then there's no alpha there, so that's just still just f triple prime like so. And now let's just take out a constant factor of an eighth. So if we take out this eighth here, then if you sort of take out an eighth, we're multiplying the coefficient by an eighth. So this thing here is going to become 6. This guy here is going to become 4 times 3, which is 12. And this guy here is going to become 8. And have a look, we get what's inside the square brackets is exactly what we kind of want to get. Now, remember from our lemma, we know that h triple prime has at least 2 distinct real zeros, because h was 3 times differentiable and had at least 5 distinct real zeros. So h triple prime has at least 2 distinct real zeros, but notice this function here is positive always. E to the x over 2 divided by 8 is a positive function, so that means any zeros of this function, h triple prime, are going to be zeros of this function here. And because we know h triple prime has at least 2 distinct real zeros from our lemma, we know that this guy here, i.e. this guy here, has at least 2 distinct real zeros, and that solves our problem. I hope that's all made sense. It was a fun little Putnam problem. It was sort of a B1, so the first first problem of a day. So generally they should be on paper a bit simpler. But yeah, this involved quite a neat trick, but hopefully once you stare at it for a while, the key thing was getting this, and then the rest was essentially computation, and then sort of plugging in alpha equals a half was straightforward. Anyway, I hope you have enjoyed this video. Thank you for watching. I'll catch you in the next one. Have a great day.